Let's get started. So, as Fabian said, I recently started as a postdoc at the Department of Earth Sciences at the University of Oxford, working on Central Asian faults, but I only recently completed my PhD at the University of Melbourne. So that's what I'm presenting today, talking about Australian surface structuring earthquakes. I just want to start by thanking a few co-authors and contributors. So first off, Mark Quigley and Dan Clark have contributed a heap of work and ideas that pop up throughout this talk. Mark was my PhD supervisor, and Dan Clark is a co-author at Geoscience Australia. I also want to thank Mike Sanderford, my secondary supervisor, and co-author Januka, whose work also appears in here, and Ryan Gold at the USGS, whose work appears, and various other co-authors across University of Melbourne, Geoscience Australia, and other institutes. I also like to start my talks by acknowledging the traditional custodians of the land on which the data that I'm presenting were collected. That might just be from publications or my own fieldwork. It includes the Wurundjeri people of Melbourne, where I lived and worked for so many years, the APY people of the Central Deserts, the Noongar people of WA, the Warramunga people of Tennant Creek, the Murriwong and Gudgerabang people of Kununurra and sort of northern WA. And I just want to acknowledge that the land on which we do our work was never ceded by those people. So we're going to cover a lot of ground today, talking about Australian surface ruptures, what they tell us about intraplate faults and seismic hazard, and just generally what they can tell us about reverse earthquake strong ground motions. I assume that most of you don't know much about Australian surface ruptures, so I'm going to start with an intro to Australian earthquakes, and then I'm going to go into the bulk of the talk is going to be about Australian surface rupturing earthquakes, starting with what we recognise as bedrock controls on that faulting, talking about how we measure the length and offsets of those, and then finally talking about recurrence on those faults. Then I'm going to sort of share with you some weird and wonderful work we did where we turned into accidental seismologists by asking the question, if a rock flips in the desert and nobody was there to see it, did it record an earthquake? I'm going to try to convince you that yes, it did. And finally, I'll just give you an overview of where the current status of Australian seismic hazard and intraplate stress studies lie, and some ongoing questions that we're asking about Australian earthquakes. So this is just a brief intro to Australian seismic tectonics, or as I like to say, yes, Australia does have earthquakes, which is the never-ending response when I tell people what I do or what I did. So Australia sits on the Indo-Australian plate. It's moving northwards by about 7 centimetres a year, which is incredibly fast. It's the fastest moving continent, but we're incredibly stable internally. We have no active plate boundaries around the continent here, but we still have earthquakes. So they're quite an intriguing little puzzle. There's a lot to take in on this slide, but I'll walk you through it. Just thinking about the neotectonic period in Australia. So we define active faulting and folding as anything that aligns with the current stress field in the crust. So that stress field has been in place since about 3 million years, when the active plate boundaries on the Indo-Australian plate sort of locked in and locked in the orientation of the crustal stress field in Australia. So that crustal stress are these black lines you see going across the map here. It's the direction of compressive horizontal stress in the crust as measured by borehole breakouts and focal mechanisms. And you can see that it sort of deviates across the country. It's not in the direction of our plate motion, which is to the north. And those deviations are there because this crustal stress field in Australia is controlled by far field plate boundary forces. So the Indo-Australian plate has the Himalayan collision, the Indonesian subduction zone, PNG and New Zealand collisional zones across its borders. And those collisional zones are creating this compressional stress field through our crust in Australia. So active faults and folds generally align with that compressive stress. And it means that we get mostly reverse earthquakes through the onshore crust. We're defined as an intraplate region because we don't have any active plate boundaries. So the edge of the continental shelf, so the onshore continent and then the continental shelf just goes off into the oceanic crust. There's no active plate boundaries. And we also get this definition of stable continental region, which is this sort of subcategory that was defined in the mid-90s for these non-active intraplate regions, these really old, really cratonic areas of the intraplate crust, which are theoretically stable. I want to take you through 3 geological divisions that we sort of use when we think about neotectonics in Australia and earthquakes in Australia. The first is this grey around the edge of the continent. That's mostly offshore extensional basins or offshore extensional basins from failed rifting when we rifted away from Gondwana. I tend not to think about the offshore stuff. I deal with the onshore stuff in my work. So I'm just going to talk you through these two classifications. In the east here, we have the non-extended Phanerozoic crust. So that's the youngest portion of the crust. It's still pretty old. It's sort of the east of Australia was sort of pushed on through the mid-Paleozoic. So still pretty old, but it's the youngest part of the continent. We have the largest topography through here, the Great Dividing Range, and we have higher geomorphic rates through here. So higher erosion rates because we have this topography and we have more active river systems. The central and west of the country is where I tend to focus my work, and this is the Precambrian crust. So it's the oldest portion of the continent. It's all of these Archean cratons surrounded by Proterozoic mobile belts, so these orogenic belts from the Proterozoic, and a bunch of superbasin from the Proterozoic. So incredibly old. A lot of the topography we see through this crust is relic topography, so these Proterozoic origins, these mountain ranges that were very large have just been sitting around and eroding slowly away to leave the cause of those mountain ranges as topography. We have incredibly low erosion rates through the central and west, so it's sort of like 1 to 5 meters per million years, which you can compare to sort of 20 to 50 meters per million years in the east. So relatively different crustal properties between the east and the center and west. So thinking about the new tectonic features that we recognize, all these red lines here are captured in Geoscience Australia's active neotectonic fault database. And I'll just check the chats. Yeah. And so this database is publicly available online. I just want to focus on the east first again. So in the east, we see a lot of these red lines have offset old basement over the top of quaternary sediments, or they've folded quaternary sediments, or they've offset rivers. So the Murray River has been dammed a few times by active fault movement. So we see these things building topography. Through the Flinders Ranges, we see like tens to hundreds of meters of topography being built across these active faults. So we clearly know that these are active. We know that they're hosting recurrent earthquakes through time, through the neotectonic period, because they're building that topography. It's sort of more traditional tectonic geomorphology signals. Through the central and western part of the country, it's a bit of a different story. Most of these red lines were drawn by SRTM elevation models. So that's satellite elevation models. And because of the resolution of that model, most of these red lines represent offsets that are like 2 to 3 meters or more across a linear feature. And so that implies that most of these things that we've drawn here from the elevation models have hosted more than one event. They have to have hosted 2 or 3 earthquakes to create that sort of offset. But we don't see the sort of topography that's being built in Eastern Australia through the central and west. They might host 2 to 3 meters of offset, but generally a little bit less. And a lot of these haven't been investigated paleoseismically just because they're so remote. So we have this kind of variance in the eastern part of the country where we see sort of traditional fault recurrence, and then in the center and west, we don't see that sort of topography. We see them sort of more widely spaced. And finally, just thinking about the historic earthquake catalogue, this is just onshore earthquakes. So historically, we can see 4 main zones of seismicity popping out. One of them is the Northwest Shelf. I've only shown onshore earthquakes, so that looks a bit bare. In terms of onshore seismic zones, we have the Southwest seismic zone near Perth, the Flinders Ranges seismic zone near Adelaide, and the Southeast seismic zone near Melbourne, Canberra, Sydney. So we just happen to have built all of our big cities right next door to these seismic zones, which is a bit of a bother. And 2 of these seismic zones are located on top of where we see those active faults, building topography and things like that, so that makes sense. The Southwest seismic zone isn't necessarily. We don't see really all that much topography being built there, and I'm going to talk a lot more about the earthquakes in through here. Historically, all of our magnitude 6 and above events, we've had 8 of them so far since 1940. They've all happened in the central and western part of the country. So again, we haven't seen any big or moderate to large magnitude earthquakes on the faults that we see that can host them. Those faults down there theoretically could host up to a magnitude 7.5-ish. But we haven't seen those historically. We've only seen them happen out in the middle of nowhere where we didn't know that faults were existent, and they didn't really have any pre-seismicity that would have suggested that they were about to host a magnitude 6 earthquake. So again, it's this bit of a puzzle between the east and the center and west of the country. So now I'm going to get into the bulk of the talk, and this is about Australian surface rupturing earthquakes. So just so that we're all on the same page, because I know that COMET includes volcanologists as well as earthquake scientists, this is what I mean by surface rupture. So in Australia, we have mostly reverse earthquakes. Theoretically, that means that an earthquake starts, the hypocenter starts down on a fault somewhere, and then depending on how shallow the earthquake starts and a bunch of other factors, that earthquake may rupture up and propagate up along a fault system and reach the surface, offsetting the hanging wall over the footwall. So this is the hanging wall over the footwall, permanently deforming that land surface through this earthquake activity. So that's just getting us all on the same page. And these things are important to measure and to map out and to understand, because they theoretically show us the direct link to the faults at depth, which we otherwise can't necessarily image just using traditional seismological sort of data. And so understanding the fault systems helps us understand the seismic hazard in these regions. So historically, Australia's had 11 surface rupturing earthquakes since 1968 to 2018. And that's quite a high number considering we're this stable continental region and intraplate area. So all of these 11 events happened in the central and western part of the country. No surprises there, that's why I work there. And they range in magnitude up to magnitude 6.6 and down to quite low magnitudes like this 4.7 Katanning event. And these earthquakes are all relatively shallow. So we have poor seismological data for these because the instruments, seismological instruments, were generally over 100 kilometers away. So the locations on the epicenters aren't very good, the depths aren't very good, but generally we think that these earthquakes started at less than 6 kilometers depth and probably something more like less than 3 kilometers depth, but it's hard to say. So I really wanted to, last year I wrote this review paper looking back at all of the historic literature I could get my hands on describing these earthquakes, because I wanted to learn about what we could say about active faulting in Australia based on decades of earthquake science since the first of these events happened in 1968. So what I did is I digitized all the historic data sets that included all the vertical offsets, lateral offsets, dip measurements, all the focal mechanisms, all the epicenters I could get my hands on, any sort of offset data in the surveying, anything I could get my hands on. I digitized that to try to understand what we could say about these earthquakes in the modern sort of earthquake science period. And so it's, as part of that, I also created a bunch of new net slip measurements to make these things consistent with sort of global data sets for surface ruptures, where generally you might have net slip being used instead of vertical offset measurements, which is what historically had been inputted from Australian data. And so I created these new net slip measurements, and I then also re-measured all the lengths of these surface ruptures. So they were all measured consistently, because between 1968 to 2018, they'd all been measured by different researchers with different intents and different data sets. So I re-measured them all. And in 2018, Geoscience Australia also did a big revision of the moment magnitude database. So we had these 3 new data sets, the length, the net slip, and the moment magnitude. And I just asked a simple question, well, does that compare to what we think about Australian data historically? So one of the reasons we study surface rupturing earthquakes is to get these length and offset and moment magnitude data that we can build into scaling relationships, so that when we look at a paleoseismic rupture, we can say, well, if it's 20 kilometers long, we expect this much displacement from this big of an earthquake. But when we look at the new data for Australian earthquakes that were measured in this consistent way, these are all of them coming down here. You can see that they don't necessarily plot with the other reverse earthquakes, and this is just the traditional Wells and Coppersmith relationships. So we sort of have to start questioning, and this is across the board with a bunch of other scaling relationships. The new data just don't plot very well. So we sort of have to question what that historic data sort of means and how we build our new generation scaling relationships for these earthquakes in particular, but reverse earthquakes generally. So now I just want to take a little bit of time to talk about one of the main motivations for me to look back at all of this data was simply the question of why were all these surface structures so curvy? Why were they so concave, and some of them were convex, and some of them, like the Kadu earthquake, were just a mess of surface structures. And we couldn't fit a simple planar fault, which is what seismologists so commonly like to do. They like to imagine that faults are this nice planar rectangle, and you just can't fit that to most of these surface structures. So something else is going on with these fault systems to create these non-linear structures. And I really wanted to understand what was going on at depth to manifest at the surface as these really odd concave shapes. So I'm just going to take you through sort of the sort of data that I was looking at, and I did this across the board, but I'm just going to take you through the Marriott Creek example. This is a very remote earthquake, so out in the central deserts of Australia in 1986. A magnitude 5.7, and the surface rupture is about 13 kilometers long end to end. And so despite this earthquake being incredibly remote, a surveyor went out quite shortly afterwards to survey along the length and the offsets of the Marriott Creek earthquake. So we have quite a good record of what the offsets were and what the surface structure looks like, which is quite handy. But I wanted to understand if we see this really, they called it a boomerang shape in the original literature, which is fair. It's super concave and you can't fit a single plane to that. So I wanted to understand what might be happening in the basement geology to try to figure out whether that represents what's going on at the surface. So I looked first off at this geophysical data that we have across Australia. This is just the magnetic lineament data. So you can see all these lineaments in the bedrocks at some depth in this geophysical data. We can't say what depths they are necessarily without a bunch of extra geophysical work. But we can see that the lineaments, there's a bunch of lineaments that match the orientations of the surface structure of the surface. So we see this sort of east-westish limb, we see this northwest-southeast limb, and we see this north-south limb. And we can match basement structures to each of those orientations. Unfortunately, with the geophysics, we can't say for sure like the surface rupture is directly related to these things at depth because the geophysics is open to interpretation. So I wanted to get a little bit more data. That included bedrock geology at the surface. There weren't particularly good geological maps for the Marriott Creek region. So I simply looked at visual satellite imagery and found any bedrock surfaces that I could, or bedrock outcrops at the surface, and mapped out lineaments. So foliation planes, dike intrusions, fault planes, anything I could see in these bedrock outcrops. And when I plugged those into a rose diagram, there are three main orientations of the lineaments in the bedrock at the surface, and they match really well with the three orientations that we see at the surface rupture. So there's this additional information suggesting that while we see these bedrock structures at depth, we see them at the surface, potentially the surface structure orientation is being controlled by these three main orientations that we see in the bedrock. And just to add a last piece of evidence for this, there was some trenching work done across the Marriott Creek surface structure in the central area here where we see the maximum slip. And in this trench, in these trenches, they found bedrock on both sides that hadn't been offset previously, which I'm going to come back to in a little while. But for the purposes here, they found this bedrock on both sides, and they realized that the historic surface structure had cut through this Precambrian fault system. It was this lower crustal, very wide thrust system, and the historic rupture had exploited some of those structures to reach the surface. So it added a little bit more evidence to suggest that while we see these bedrock sort of structures, whether they're foliations or dike intrusions or faults, we see those things in the geophysics, we see them at the surface, and we see them in the trenches. So we conclude that chances are this surface structure is controlled by the bedrock orientations, these pre-existing bedrock planar features, whether they're faults or foliations or dike intrusions or whatever, they're pre-existing planar features that control the earthquake that happened historically. So the earthquake initiates on one of these bedrock structures and then ruptures across multiple other intersecting bedrock structures to reach the surface as this really curvy surface rupture. So in this case, we defined three bedrock faults that failed in the historic earthquake. So just to add a little bit more data to that, we'll look at the Peeterman earthquake, which again is a very remote earthquake in the central deserts of Australia. I spent a lot of time on this earthquake because it happened a few months into my PhD, which was incredibly lucky. So it was a magnitude 6.1 earthquake, and it created this surface structure through the central deserts. And the region that it ruptured has all this bedrock at the surface that's these really well foliated myelinites. So it's this granitic myelinite that formed in the Precambrian, and it's really foliated. And you can see this post-event satellite image here shows the surface structure coming through, and it shows all this bedrock at the surface that sort of lines up these sort of white things here. They line up pretty well with the surface structure, so they share the same strike. And when we got into the field, in certain locations, we could see the surface structure itself, which is what Dan is standing on here, this sort of broken up ground, the surface rupture actually abuts onto some of these bedrock outcrops, which also share the same dip as the surface structure. So there's this really strong connection between the surface structure strike and dip and the bedrock strike and dip, which again suggests that probably this surface structure was exploiting a pre-existing bedrock foliation plane. We see a bit more evidence of this in the aftershock distribution and the trenching. So the trenches also preserve this sort of 25 to 35 degree dip in the sediments, which aligns well with the bedrock outcrops that we map across the region. And we also had this high resolution aftershock network in place. And when you look at the depths of those aftershocks, they also define this sort of 30-degree dipping plane, which is consistent again with the bedrock orientations that we see across this region. So it's just a bunch of evidence to suggest that yes, probably this earthquake started on a pre-existing bedrock structure and ruptured to the surface along that structure. So we do this across all of the historic ruptures, and in every case, we see evidence to suggest that these surface ruptures, the earthquake started on some sort of pre-existing bedrock structure and ruptured to the surface along that structure or along multiple intersecting structures. So in 6 of the 11 events, we can define multifault ruptures. So like we did in the Marriott Creek, where we said that there were three faults that ruptured, we can do that across the board, and we can define that a lot of these bedrock structures failed as a multi-fault rupture system. So the earthquake starts on one fault and then cascades across all of these bedrock structures. And if we compare that to sort of a global database that some colleagues put together a few years ago, we have magnitude along here, a number of faults that were interpreted from these earthquakes globally. And you can see that some of these Australian earthquakes map as really quite complex faults for their magnitudes, right? So they're the highest number of faults for their magnitude. So quite interesting fault dynamics going on in this Australian crust. All right, I want to switch to something, to just really quick sort of bits and pieces that we're starting to think about for Australian earthquakes. And that's this idea of visible surface structure versus detectable surface structure. So we have INSAR over 3 of the historic events, the Peeterman, the Katanning, and the Lake Newar. So in the case of the Peeterman, these black lines here are what we could see visibly. That was with our eyes, it was with a drone DEM, and it was in worldview satellite imagery. So visible data that we could see at the surface that showed that there was a surface structure there. And if you compare those black lines with the INSAR trace, you can see that we don't always pick up the deformation that the INSAR sees. So in this case, the INSAR defined a surface structure length of about 21 kilometers, but the visible surface structure only defined 20 kilometers, and it was really segmented. And partly that was because there were sand dunes that the surface structure just couldn't get through. It just can't get through that, that sand material. So in a more extreme case, the 4.7 Katanning earthquake, quite a small magnitude earthquake, the report suggests that there was about 300 meters of visible offset in this farmer's field. So he noticed that the ground had changed after the earthquake, but the INSAR defines about 2.5 kilometers of rupture length. So this is, if we were going by just the visible offset, we would severely underestimate what the length of this rupture was. But with the INSAR, we can see that it's actually much longer. So this might not be important everywhere in the world, but particularly in these sort of cratonic, thick crust, shallow earthquake events, we need to be thinking about, well, are we sure that the historic length mapping actually captured the full length of the fault? INSAR is giving us this information that shows that we can capture this sort of distributed and full deformation envelope. So we have colleagues at Geoscience Australia who are trying to work up some scaling relationships that might relate to what we see in visible versus detectable. All right, now thinking about offset. So we're back on the Peeterman earthquake from 2016, and Ryan Gold at the USGS put this paper together that we helped to co-author a few years ago. And he looked at what he could see in the INSAR offsets that I showed earlier. And then he created this DM of difference. So he took 2 satellite images from before the earthquake, 2 satellite images from after the earthquake, created DEMs before and after, and then difference those DEMs to try to understand the offset envelope around the surface structure. And we compared it with GPS offsets that we took. Dan Clark from Geoscience Australia went out into the field with an RTK GPS, and he took spot measurements on the top of the hanging wall and on the bottom of the footwall, and he differenced those to get vertical offset measurements. And so we compare these remote sensing techniques with the field techniques. If we look at across the rupture cross sections of the DEM and the INSAR, these remote sensing techniques, we see that there's the offset captured at the surface structure itself. But these techniques are capturing offset up to like 1 kilometer away from the surface structure on the hanging wall. So there's this distributed deformation that exists on the hanging wall, which creates a total offset picture. But if we look at offset just along the rupture and we compare those INSAR and DEM offsets to what we picked up in the field, which are all these dots, you can see that these dots well underrepresent what the total offset was because we're not picking up that distributed deformation when we go into the field. So theoretically in the field, we can't just take spot measurements. We need to be thinking about how to get across that distributed deformation field, which might be up to 1 kilometer or more away from the surface structure itself, if we actually want to be measuring the total offset of this fault. All right, and finally for surface ruptures, I want to end with how do we define recurrence for all of these 11 events? So slip rates are really important for seismic hazard. The theory is that if you dig a trench and you see multiple offsets, then you can decide, you can date them, try to date them, and knowing the amount of slip and then the date, you can create a slip rate. And those are primary inputs into a seismic hazard map so that you know how fast these faults are slipping. So I wanted to find evidence of recurrence. So I looked in the literature, and a bunch of these earthquakes have been trenched in quite good detail, and some of them have been trenched by just hand trenches, and some of them, it seems they just dug some holes. It wasn't necessarily clear what they were doing. But in all cases, all of these trenches, and there are more, these are just some examples, all of these trenches expose either bedrock on both sides of the trench or quaternary or tertiary sediments on both sides of the trench. And in all cases, there's no evidence of pre-existing rupture on the historic fault. So where we expose bedrock at either side, that suggests that there's been no pre-existing rupture for a very long time because this bedrock is all generally Precambrian. When we expose quaternary or tertiary sediments, we might not be going that far back in time, but those sediments still don't preserve any surface ruptures. So historically, this was suggested that maybe these faults are hosting recurrence on greater than 100,000 year timescales, but we wanted to get into some more detail and do some more detailed work if we could. So again, we looked at the Peeterman earthquake. This is just the surface trace running nice and straight through this bedrock dominated landscape in this particular case. And so we dug 2 trenches, which is fairly traditional, to try to get the geometry and any prior offsets. And in both cases, we dug down to this hard calcrete layer, which formed in situ of these aeolian sediments at the surface. And in both cases, we found no pre-existing ruptures on the historic fault. So the calcrete preserves no offset, and the aeolian sediments preserve no offset. So we got an OSL date from one of those trenches, and it says that the aeolian sediment is about 10,500 years old. So any prior rupture has to be older than that, but we sort of assumed that anyway. So we want to go back in time further. So the first thing we tried to do was compare pre-earthquake DEMs with the post-earthquake DEMs that Ryan Gold made for his paper. And we wanted to see if there was any geomorphic or topographic evidence of the scarp in this landscape. So if we draw cross sections across these DEMs, within the resolution of those DEMs, we see no evidence of offset before this historic earthquake. So if a scarp did exist before this earthquake, it's been completely eroded out of the landscape and out of that bedrock before the historic earthquake. We also looked at geomorphology of the region. If you offset the hanging wall of the footwall, you might change the drainage systems. And we see no evidence that there's been changes to the drainage. We see no migrating nick points. So there's no evidence in the landscape currently that there's been a pre-existing scarp. And trying to sort of put some constraints on that, we did this thing with beryllium 10 erosion rates. So because this landscape is incredibly old, it's very flat, it's eroding really slowly, all these granitic bedrock outcrops preserve erosion rates that are quite low. And theoretically, if you offset the hanging wall of the footwall, just locally, you're going to increase the erosion rate on the hanging wall versus the footwall because you've created this offset that needs to be readjusted. And we also observed a bunch of these bedrock outcrops in the near field had been sort of fractured. On the larger outcrops, we saw a bunch of stuff that had been lost due to shaking. So theoretically, in the near field, you might expect those granite outcrops to preserve higher erosion rates than the far field if there was an earthquake within the time constraints that we can place using these beryllium 10 erosion rates. So the erosion rates in this landscape can take us back to about 400,000 years. That's the averaging period of them. So we can sort of try to see if there's any offsets preserved in the erosion rates within the last 400,000 years. So we sampled really close to the surface structure, and we sampled at sort of 50 kilometers distance, and we try to compare those things. And when we got the data back, this is a graph of the erosion rate versus the distance from the surface structure on a log scale. And we see no real difference in the erosion rates close to the surface structure relative to those far field rates. And we also see no difference in the hanging wall versus the footwall rates. So these are the black versus the gray data. So within the error and the assumptions of our erosion rate data, we see no evidence that the erosion rates are preserving higher erosion due to any seismic activity, due to either shaking or the direct offset of the hanging wall. So that takes us back to about 400,000 years. There's been no evidence in these rocks preserved of any sort of seismic event for that time. And we can also ask the question, well, if there was no pre-existing scarp, if there was a prior event, it must have completely eroded away, and we have these bedrock outcrop erosion rates, so we can sort of think about how long does a scarp exist in this landscape. And that takes us to, a scarp should exist for about 400,000 years to 1 million years. So we're pushing back as best we can any recurrence to sort of over 1 million years ago. And the easiest way to explain this is that this fault just hasn't hosted an earthquake previously. So before the historic earthquake, before 2016, there was a foliation plane sitting in the bedrock. We don't know whether it had hosted slip or not in the Precambrian, but certainly within the neotectonic period, chances are it hasn't hosted any slip. So therefore, it technically isn't an active fault before the earthquake in 2016. So this raises a bunch of problems for us in terms of seismic hazard and understanding faults in Australia. So in the central and west, based on the historic data and historic surface structures, it looks like we can have earthquakes that show no recurrence, and they may just be one-off events. We can't really say for sure, but what we can say is that if they're not preserved in the landscape, we can't recognize them as active faults. But we do recognize active faults in the east of Australia. So just to show you an example, the Lake George fault is down here where that star is, right next to our capital city, Canberra. So Australia's Parliament House is just tucked in here. And the Lake George fault offsets sediments by 250 metres. So Dan Clark at Geoscience Australia and various colleagues have been working on this fault. And they show that it goes through these active periods where it hosts offsets with a slip rate of maybe 1 millimetre per year, but then it sort of shuts down for an unknown amount of time or a known amount of time. And so that long-term rate is much, much lower. So even though we see these active faults preserved in the landscape and preserved in the topography in Eastern Australia, we don't know if we're in an active period or if we're in an off period. So seismic hazard in this case is still quite hard to do. But then compare that with the central and west of the country, where, you know, the Lake Newer fault in 2018, clearly this is not hosting much offset. We have no topography preserved across this, and we have no way of recognizing it in the landscape before it hosts this earthquake, and potentially it just has no slip rate. Potentially it hasn't happened before. So we have these two sets of sort of fault activity, and we're starting to ask this question, well, if we have this non-homogeneous stable continental region crust, how do we build that into seismic hazards? Clearly the crust has different properties across the country. All right, thanks for sticking with me. Take a deep breath. We're going to swap focus into these things that I like to call flip chips. So this is a bit of fun for your presentation today. Technically, I should call them co-seismically displaced rock fragments. So by chips, I just mean these rock fragments. The bedrock in the Peeterman earthquake is eroding by this sort of exfoliation. So it creates all of these bedrock chips that look a little bit like this or smaller. And in the near field of the Peeterman earthquake, we kept seeing these chips that had been displaced by the earthquake. And we knew that they were fairly fresh in a lot of cases because they'd fallen on top of fresh vegetation, and they'd killed the vegetation, or they'd exposed insect castings, all sorts of things. So a lot of these we interpret as co-seismic. Some of them might be from animal hooves, but we have 1,500 of these things documented. So chances are we're picking up a co-seismic signal in amongst any noise. This is what they look like. So it's quite easy to pick them in the field because the desert rock has this really strong color to it, the patina, and if you flip it over, it's a different color. So literally just we walked across the landscape and we put these back together like jigsaw puzzles. And in some cases they went up to 1 meter along these flat surfaces. So you can imagine you have to have some sort of energy input in order to get that trajectory. In some cases they went upslope of their original location. So again, we infer that there's this seismic energy that's making these things move. So theoretically we have 1,500 little instrumental points, so acting as little proto or sort of seismometers all across the region. So it covers about 100 kilometers squared of the near field, less than 5 kilometers from the Peeterman rupture. So the questions that we're trying to ask in this data is, do these rocks record seismic seismological processes? Do they record the near field strong ground motions in the absence of instrumental data? So I just want you to take away from these plots, these rose diagrams show in the orange, the number of rocks that traveled in a certain direction at a certain location. So in the hanging wall, in the near field on the hanging wall, we see a lot of the rocks traveling away from the surface structure, which is what we might expect because in a reverse earthquake, the hanging wall gets pushed up and it has this really strong motion. So the fault itself is moving up. We call that the fling step motion, and it also has these strong ground motions that might be directional. But if you push the rock up, we theoretically think that if the bedrock goes up this way towards the direction of rupture, then the rocks on top of it might fling away the other way. So we think we're seeing that in the data. The footwall in a reverse earthquake doesn't necessarily move as much. It doesn't have as much energy in it. So we see no consistent motion in the footwall, which is again what we might expect from just the theory of this faulting. And as you get to the edges of the rupture, we see less rocks moving, but we also see less directionality to them. So we think that we have this sort of seismic signal coming out through these rocks. We really wanted to test that if possible. So we're working on a way to test that against seismological models. My colleague Januka at the University of Melbourne ran some finite fault models for me, modeling bilateral rupture and 2 unilateral rupture models on the Peeterman earthquake. And we take out from those models the direction of static and dynamic displacement. So that just means the shaking. And we try to compare that with the rock data. So we're currently in the process of thinking about whether the seismic data in blue and black here represent what the rocks are doing. And in terms of this location, the bilateral rupture seems to correspond with what our interpretation is, where the seismological data goes in one direction and the rocks go in the opposite direction. But we're currently working on it. But it is an important question to ask. These are just some models that the very smart people in California and other places put together, modeling the near field strong ground motions for a reverse earthquake similar to the Peeterman earthquake. And it's based on instrumental records that are very sparse, right? There's only 15 instrumental records in the near field of reverse earthquakes globally. So we have 1,500 potentially near field records, and these guys are working on just 15. So you can see that there's quite diverse motions that they're modeling. We're hoping that our rocks might be able to help constrain some of these models for the near field or reverse earthquakes. And it's particularly important for reverse earthquakes for engineering, because as we've seen in a bunch of cases, including the Kashmir earthquake in Pakistan, the hanging wall gets offset and it experiences this really intense shaking in the near field compared to the footwall, which you see here, which is barely touched. So if you're engineering in the hanging wall of a known reverse earthquake, you need to know what the strong ground motions look like. So we're hoping that in Australia, we have this unique record of like environmental and geological damage in the near field, which might help boost the instrumental records globally. All right, thanks for sticking with me. We're nearly there. So number one summary is, I hope I've convinced you that Australia provides this cool record of near field strong ground motions for reverse earthquakes. Hopefully we can use that to try to understand what's going on for engineering and protect anyone living on the hanging wall of the reverse earthquake globally. I want to ask these big questions about how do we even make a hazard map in Australia? So I talked you through the fact that in the central and west of the country, it seems like we have faults that might not host earthquakes previously. But in the east, we have recurrence, but it's sort of in these active and non-active periods. How do we take that geological data and use what is quite a short instrumental record, about 120 years, and make a seismic hazard map that protects communities? The good people at Geoscience Australia put this hazard map together in 2018, and it used as much of cutting edge data and science as they possibly could. But it still relies on the assumption that faults have slip rates. And so if we find that faults don't have slip rates in some areas, that's sort of a bother. So we need to figure out what the best approach is for these stable continental regions, for these intraplate regions where these assumptions might break down. We don't really know. And finally, I want to leave you with the big tectonic question of why are these surface ruptures happening there and why then? We don't have an answer to this. It's an ongoing question. If you look at the locations of these surface ruptures, some of them are very coincident with these really big gravitational anomalies that we see in the crust, in the Precambrian crust. So the Peeterman earthquake and various other earthquakes were in the hanging wall of this really big Precambrian thrust fault that to this day hosts a 30-kilometer offset of the Moho. So quite a big gravitational anomaly, but clearly that thing is too big to rupture in an earthquake currently. So maybe it's just localizing stresses and strain and releasing as earthquakes, small earthquakes on bedrock structures close to this. That's the current theory, but we sort of have to test that, and we sort of have to understand why all of the faults are happening where they're happening in Australia, because it does have applications for how we think about other stable continental regions, so sort of in Canada and the US and parts of Europe, and also just intraplate regions generally, so maybe Central Asia. What can we learn from these Australian earthquakes that might be applicable to these other areas on the globe? And that's where I want to leave you for today. So thank you so much for listening, and I'm happy to take questions.
Thank you, Tamarah. So yeah, it's time for questions. So how we do it is usually you just have to type in the chat, and we'll take some questions for the next 10-15 minutes. I had a question about the, can you go back to the distribution between the orientation of the rocks and
Oh yeah.
of the chips? Yeah, this one.
Yep.
Next one? Yeah.
Oh, this one here? Oh, no, this one.
Yeah, exactly.
Yep.
I wanted to, can you tell us a bit more, what's the difference between the three, like I, double I, and the different like mods that you find? Yeah.
Yeah, so this is quite a complex little set of graphs. So what Januka did is he ran these finite fault models where the earthquake starts either in the center and goes outwards, or starts on one end and goes along the other way. And he extracted the dynamic motion, which is the waves of the earthquake, and the static motion, which is that fault offset that I was talking about.
Mm-hmm.
And he finds out what direction the maximum of that is in a bearing, so 0 to 360. And then we just compare, so that's the blue and the black here. We compare it to the red. And so the II here is where I see things in the opposite direction. So the strong ground motions look like they're going in the opposite direction to the rocks, or where we see peaks that don't seem to correspond to any rock motions, and things like that. So doing that across every location, we have 170 of these graphs, trying to figure out whether we can see patterns in what the seismic data suggests should happen and what the rocks are recording is happening, to see what we can say about that. All right.
Okay. Thank you.
That's okay. I'm going to get to some of these questions.
Yeah, you can take it. Yeah.
So, Sam, do you have any views on why all the earthquakes are so shallow? Do you think there can be deep earthquakes? Within the central and west of the continent where the surface structures is, there have been some deep earthquakes recorded historically, so up to about 30 kilometers depth. Clearly, they're not rupturing the surface, they're just too deep, and they're sort of magnitude 6s. I can't explain to you why they're so shallow. I think I would need my seismologist hat on to do that off the cuff. But we do tend to see those quite shallow earthquakes in that very old, thick, brittle crust where the bedrock is all the way to the surface, but not necessarily the same in the east of Australia. Aaron asks, is there a relative change to more transcurrent motion in north central region where max horizontal stress is oblique to faults? I'm not sure I understand the start of that question. For the surface structuring earthquakes, the maximum compressive stress was basically perpendicular to all of the faults that ruptured. So that's what we would expect. All the faults that have ruptured historically ruptured pretty much perpendicular to the stress in those locations. And of course, the stress field, it deviates all over the country. So, yeah, that's why they're different orientations depending on where you are. I might just skip to the next one. Is there conjugate faulting in some of the curved ruptures? Maybe, yes. But also, if we think that the earthquakes are rupturing on pre-existing bedrock structures, the faulting sort of depends, therefore, on what the structures in the bedrock are. So if there are conjugate structures in the bedrock, potentially the quake might rupture those conjugate structures. If they're just intersecting, then maybe no. I think these earthquakes are, my personal opinion is that these earthquakes were controlled by what was already in the crust. So there's no real, that's what's controlling it rather than necessarily any conjugate faulting from the earthquake mechanisms. Thomas asked, did you check for flipped rocks away from the faults as a control of how many might be due to animals? Yes. So when we were collecting the beryllium 10 rock samples from all over the region, we stopped wherever we could to look for flip chips, and we didn't see any flip chips really at any distance. As we got closer to the surface structure, we started to see them, and when we got within 5 kilometers, they were everywhere. So that's how we know that they're co-seismic. Some of that data may be by animals, but we don't think much of it is. Can you repeat, please, which are the trajectories of the sigma 1 axes within Australia? I'll just go way back and put it on the screen so you guys can all look at it if you have those questions. So the direction of maximum compressive stress in Australia is all over the place, really, depending on where you are. It's quite easy to perturb that stress field. If you build a dam in Australia, you increase the normal stress and you create a few little earthquakes. And you know, this data comes from fairly sparse borehole breakouts and focal mechanisms. So locally it might deviate a little bit, but that's what we think is going on. Bing Ming says, how the orientation of historic rupture are compared with the regional stress field. Some ruptures orientations have 9-degree strikes change. Like I answered earlier, in all cases, so the Marriott Creek earthquake, for instance, 2 of the limbs are not orientated to the stress field, but the one that hosted the maximum slip in the middle is orientated to the stress field. So it's perpendicular to the stress field, so that makes sense. I think that the earthquake probably initiated on one of those sort of not as well orientated faults, and then hit a bedrock structure that was perfectly orientated, and then ruptured up along all 3 earthquakes, all 3 faults. So in all cases, the faults are orientated perpendicular to the stress field or close enough. Aaron's asked a second question. Do you see a change in ground displacement in both geomorphology as well as INSAR? I'm not sure I understand what that question is meaning. Perhaps you could rephrase it. I'll try to get to some more. Antonio says, thanks for the presentation. Have you tried to plot earthquake location on gravity anomaly maps, or I studied gravity anomaly maps? Yes, I'm not an expert in geophysical data. And a bit of the problem with the Australian earthquake locations is we know that a lot of them are mislocated because the instruments are so far away from the earthquakes. So in the case of the Marriott Creek earthquake, the epicenter is 30 kilometers away from the surface rupture, but the uncertainty is only 10 kilometers because that's an internal uncertainty. But we know that the epicenter has to be co-located with the surface rupture. So it's mislocated by maybe 20 kilometers. So there is a little bit of bother trying to locate epicenters onto geophysical structures just because some of the data is not particularly accurate. But that is something to maybe think about. And I mean, I think that there is future research into how earthquakes and faults co-locate onto those gravity anomaly maps, but I don't really know how to tackle the question. I'd love it if someone could help. Hybo says, I have one question. The trench suggests no more earthquakes was recorded. Did you have the accumulation slip distribution of this fault and compare it with the most recent surface rupture? So in all cases, there was no pre-existing slip distribution because there was no pre-existing offset at the surface. And so it was just flat land before the historic earthquake. So we have no accumulated slip because in all cases, we can't see any prior slip. So we can't compare that to the surface rupture. Laura asks, what is the minimum geodetic strain rate? Oh, this is something that I forgot to cover. Geoscience Australia's had GPS instruments out trying to measure a strain rate since the late 90s, and so far they haven't moved enough for us to have a strain rate in Australia. There are some other estimates of strain rate, but we don't have any from the GPS instruments yet. I guess it's just too slow, so we don't have a strain rate to work with. But if someone can come up with one, that'd be great. Elliot asks, do you have a view to share on the adjustment to lower seismic hazard for Australia as seen in the global hazard map shown on your last slide? Do you think it now may be understating the hazard? So the seismic hazard map for Australia is quite difficult. And my colleagues at Geoscience Australia, Trevor and Dan, will be able to answer that question a lot better. I think the adjustment on the global hazard map probably relates to their work that they published in 2018, where I think the seismic hazard in some regions went down. But it depends on what question you're asking in Australia. Like, we don't necessarily, we don't have the data go very far back in time. So maybe it's unlikely that we have an earthquake under Melbourne tomorrow. But if we did, and we might, the strong ground motion is going to be quite big. So what do we do about that? We just don't have much data, but they're much better at answering that than I am. Luke asks, how do the scaling relationships that you see from earthquakes in Australia that differ from Wells and Coppersmith compare to earthquake ruptures in other stable continental regions? That's something that we'd like to investigate. We met at EGU about stable continental regions, and I think a bunch of researchers will try to work on how we think about these regions globally and what we have in the historic data. I think my bother with Wells and Coppersmith is that they use the Australian data to build their reverse earthquake data because Australia's had so many reverse earthquakes that of course you would use that data, but the point that I want to make there is that if you measure them in consistent ways, you get different data out of the earthquakes. So the data going in is not necessarily as accurate as it could be. Ashan, how are we going for time? Should I keep going?
Yeah, we may take two more questions maybe. And
okay.
As you wish, if you want to continue a little bit more.
Yeah.
It's like 54. We can, take 2-3 more questions and then we'll.
All right. I'll quickly scan down and see. Thomas asked, do you have precarious rocks, e.g. unstable ones that should fall but don't, suggesting they're on a nodal plane? I did work on precarious rocks at the start of my PhD before the Peeterman earthquake happened. In the Peeterman case, we saw a precarious rock about 20 kilometers away that just hadn't moved. So that was a bit unfortunate. So we have some ongoing questions about precarious rocks in Australia. But sorry, that probably doesn't answer your question, but we're looking at them sort of. Paul Somerville asks, earthquake occur at shallow depth. Oh, Paul knows a lot about Australian earthquakes, so I think he's answering a question from earlier. Earthquakes occur at shallow depths in cratonic regions because they are brittle all the way to the surface. Non-cratonic regions are ductile in the upper 5 kilometers, and generally earthquakes do not nucleate there. So that's an earthquake. That's an answer from Paul for the previous earthquake, previous question. Chris asks, are there any instrumentally recorded earthquake strike slip? Or is the stress field unfavorable for those? In terms of onshore earthquakes, surface rupturing earthquakes, no. I think that there are some offshore earthquakes that are strike slip, but I don't really know much about them. All right, I'll try and find one more question. Mazin asks, given the little instrumental information and uncertainty in epicentral location, do you think a more comprehensive and expensive paleoseismic investigation with more trenching and detailed mapping input can improve the seismic hazard map? Oh, that's a good question. Maybe, maybe not. Look, there are some faults in the central and west of the country that may be hosting offsets recurrently, but nobody's been out there to check it. So if we did have the money, we would love to go out and trench that. Sure, I have colleagues who do it in a heartbeat. But it's questionable about whether that money is well spent doing that, I guess, if there's nobody living out there. It's more of a tectonic question. It's more of an interest question. I think that we need more information on the faults close to sort of Melbourne, Sydney, Canberra and Adelaide. There's not that much work on those faults. So yes, I think that more money spent on trenching those things and understanding recurrence in those regions and trying to understand whether those faults, whether we can find out whether they're in an active or a non-active state, that's going to be really helpful for a seismic hazard. But again, it's really quite difficult. I think if you want to ask that question, Dan Clark at Geoscience Australia can probably give you a bit more information. He works on those southeast faults. All right, I reckon that's probably all the questions. Yeah.
I think we cover all the, most of the question. Thank you again, Tamarah, for this COMET webinar, and thanks the people remotely. I think it was a very interesting discussion, and we almost reached 100 attendees. So please stay tuned for the next COMET webinar, and you will find this one has been recorded, and the video will be posted on the COMET website and on the YouTube channel of COMET. So you can watch it later, and stay tuned for the next one, everyone. And yeah, hope to see you, all of you, later. Thanks.
Cool. Thank you, everybody. Be in touch if you have any questions.